The past 2 decades have seen the introduction of a technology that has radically changed the way in which we analyze and control the world around us. Born of parallel developments in computer architecture and integrated circuit fabrication, the microprocessor, or computer on a chip, first became a commercial reality in 1971 with the introduction of the 4-bit 4004 by a small, unknown company by the name of Intel Corporation. Other, more well-established, semiconductor firms soon followed Intel's pioneering technology, so that by the late 1970s, one could choose from a half-dozen or so microprocessor types. The 1970s also saw the growth of the number of personal computer users from a handful of hobbyists and hackers to millions of business, industrial, governmental, defense, educational, and private users now enjoying the advantages of inexpensive computing. A byproduct of microprocessor development was the microcontroller. The same fabrication techniques and programming concepts that make possible the general-purpose microprocessor also yielded the microcontroller. Microcontrollers are not as well known to the general public, or even the technical community, as are the more glamorous microprocessors. The public is, however, very well aware that something is responsible for all of the smart VCRs, clock radios, washers and dryers, video games, telephones, microwaves, TVs, automobiles, toys, vending machines, copiers, elevators, irons, and a myriad of other articles that have suddenly become intelligent and programmable. Companies are also aware that being competitive in this age of the microchip requires their products, or the machinery they use to make those products, to have some smarts. The purpose of this chapter is to introduce the concept of a microcontroller and survey a representative group. The remainder of the book will study one of the most popular types, the 8051, in detail. Microprocessors and microcontrollers. Microprocessors and microcontrollers stem from the same basic idea, are made by the same people, and are sold to the same types of system designers and programmers. What is the difference between the two? Microprocessors. A microprocessor, as the term has come to be known, is a general-purpose digital computer central processing unit, CPU. Although popularly known as a computer on a chip, the microprocessor is in no sense a complete digital computer. Figure 1.1 shows a block diagram of a microprocessor CPU, which contains an arithmetic and logic unit, ALU, a program counter, PC, a stack pointer, SP, some working registers, a clock timing circuit, and interrupt circuits. To make a complete microcomputer, one must add memory, usually read-only program memory, ROM, and random access data memory, RAM, memory decoders, an oscillator, and a number of input-output I/O devices, such as parallel and serial data ports. Additionally, special-purpose devices, such as interrupt handlers, or counters, may be added to relieve the CPU from time-consuming counting or timing chores. Equipping the microcomputer with a mass storage device, commonly a floppy disk drive, and I/O peripherals such as a keyboard and a CRT display, yields a small computer that can be applied to a range of general-purpose software applications. The key term in describing the design of the microprocessor is general purpose. The hardware design of a microprocessor CPU is arranged so that a small or very large system can be configured around the CPU as the application demands. The internal CPU architecture, as well as the resultant machine-level code that operates that architecture, is comprehensive but as flexible as possible. The prime use of a microprocessor is to fetch data, perform extensive calculations on that data, and store those calculations in a mass storage device or display the results for human use. The programs used by the microprocessor are stored in the mass storage device and loaded into RAM as the user directs. A few microprocessor programs are stored in ROM. The ROM-based programs are primarily small fixed programs that operate peripherals and other fixed devices that are connected to the system. The design of the microprocessor is driven by the desire to make it as expandable as possible in the expectation of commercial success in the marketplace. Microcontrollers. Figure 1.2 shows the block diagram of a typical microcontroller, which is a true computer on a chip. The design incorporates all of the features found in a microprocessor CPU, ALU, P, C, SP, and registers. It also has added the other features needed to make a complete computer: ROM, RAM, parallel I/O, serial I/O, counters, and a clock circuit. Like the microprocessor, a microcontroller is a general-purpose device, but one which is meant to fetch data, perform limited calculations on that data, and control its environment based on those calculations. The prime use of a microcontroller is to control the operation of a machine using a fixed program that is stored in ROM, and that does not change over the lifetime of the system. The design approach of the microcontroller mirrors that of the microprocessor. Make a single design that can be used in as many applications as possible in order to sell, hopefully, as many as possible. The microprocessor design accomplishes this goal by having a very flexible and extensive repertoire of multi-byte instructions. These instructions work in a hardware configuration that enables large amounts of memory and I/O to be connected to address and data bus pins on the integrated circuit package. Much of the activity in the microprocessor has to do with moving code and data words to and from external memory to the CPU. The architecture features working registers that can be programmed to take part in the memory access process, and the instruction set is aimed at expediting this activity in order to improve throughput. The pins that connect the microprocessor to external memory are unique, each having a single function. Data is handled in byte or larger sizes. The microcontroller design uses a much more limited set of single and double byte instructions that are used to move code and data from internal memory to the ALU. Many instructions are coupled with pins on the integrated circuit package. The pins are programmable, that is, capable of having several different functions depending upon the wishes of the programmer. The microcontroller is concerned with getting data from and to its own pins. The architecture and instruction set are optimized to handle data in bit and byte size. Comparing microprocessors and microcontrollers. The contrast between a microcontroller and a microprocessor is best exemplified by the fact that most microprocessors have many operational codes, opcodes, for moving data from external memory to the CPU. Microcontrollers may have one or two. Microprocessors may have one or two types of bit handling instructions. Microcontrollers will have many. To summarize, the microprocessor is concerned with rapid movement of code and data from external addresses to the chip. The microcontroller is concerned with rapid movement of bits within the chip. The microcontroller can function as a computer with the addition of no external digital parts. The microprocessor must have many additional parts to be operational. The Z80 and the 8051. To see the differences in concept between a microprocessor and a microcontroller, in the following table we will examine the pin configurations, architecture, and instruction sets for a very popular 8-bit microprocessor, the Zilog Z80, and an equally ubiquitous microcontroller, the 8-bit Intel 8051. Note that the point here is not to show that one design is better than the other. The two designs are intended to be used for different purposes and in different ways. For example, the Z80 has a very rich instruction set. The penalty that is paid for this abundance is the number of multi-byte instructions needed, some 71% of the total number. Each byte of a multi-byte instruction must be fetched from program memory, and each fetch takes time. This results in longer program byte counts and slower execution time versus single-byte instructions. The 8051 has a 62% multi-byte instruction content. The 8051 program is more compact and will run faster to accomplish similar tasks. The disadvantage of using a lean instruction set as in the 8051 is increased programmer effort expense to write code. This disadvantage can be overcome when writing large programs by the use of high-level languages such as BASIC and C, both of which are popular with 8051 system developers. The price paid for reducing programmer time, there is always a price, is the size of the program generated. A microcontroller survey markets for microcontrollers can run into millions of units per application. At these volumes, the microcontroller is a commodity item and must be optimized so that cost is at a minimum. Semiconductor manufacturers have produced a mind-numbing array of designs that would seem to meet almost any need. Some of the chips listed in this section are no longer in regular production. Most are current, and a few are best termed smokeware. The dreams of an aggressive marketing department. 4-bit microcontrollers. In a commodity chip, expense is represented more by the volume of the package and the number of pins it has than the amount of silicon inside. To minimize pin count and package size, it is necessary that the basic data word bit count be held to a minimum, while still enabling useful intelligence to be implemented. Although 4 bits in this era of 64-bit maximicros may seem somewhat ludicrous, one must recall that the original 4004 was a 4-bit device and all else followed. Indeed, in terms of production numbers, the 4-bit microcontroller is today the most popular micro made. The following table lists representative models from major manufacturers' data books. Many of these designs have been licensed to other vendors. These 4-bit microcontrollers are generally intended for use in large volumes as true one-chip computers. Expanding external memory, while possible, would negate the cost advantage desired. Typical applications consist of appliances and toys. Worldwide volumes run into the tens of millions. 8-bit microcontrollers. 8-bit microcontrollers represent a transition zone between the dedicated, high-volume, 4-bit microcontrollers and the high-performance 16 and 32-bit units that will conclude this chapter. 8 bits has proven to be a very useful word size for small computing tasks. Capable of 256 decimal values or 0.25% resolution, the 1-byte word is adequate for many control and monitoring applications. Serial ASCII data is also stored in byte sizes, making 8 bits the natural choice for data communications. Most integrated circuit memories and many logic functions are arranged in an 8-bit configuration that interfaces easily to data buses of 8 bits. Application volumes for 8-bit microcontrollers may be as high as the 4-bit models, or they may be very low. Application sophistication can also range from simple appliance control to high-speed machine control and data collection. For these reasons, the microcontroller vendors have established extensive families of similar models. All feature a common language, but differ in the amount of internal ROM, RAM, and other cost-sensitive features. Often, the memory can be expanded to include off-chip ROM and RAM. In some cases, the microcontroller has no onboard ROM at all, or the ROM is an electrically reprogrammable read-only memory, EPROM. The purpose of this diversity is to offer the designer a menu of similar devices that can solve almost any problem. The ROMless or EPROM versions can be used by the designer to prototype the application, and then the designer can order the ROM version in large quantities from the factory. Many times the ROM version is never used. The designer makes the ROMless or EPROM design sufficiently general so that one configuration may be used many times, or because production volumes never justify the cost of a factory ROM implementation. As a further enticement for the buyer, some families have members with fewer external pins to shrink the package and the cost. Others have special features such as analog to digital, AD, and digital to analog, DA, converters on the chip. The 8-bit arena is crowded with capable and cleverly designed contenders. This is the growth segment of the market, and the manufacturers are responding vigorously to the marketplace. The following table lists the generic family name for each chip, but keep in mind that ROMless, EPROM, and reduced pin count members of the family are also available. Each entry in the table has many variations. The total number of configurations available exceeds a total of 80 types for the 11 model numbers listed. Caution: not all of the pins can be used for general-purpose I/O in addressing external memory at the same time. The sales literature should be read with some care to see how many of the pins have more than one function. Inspection of the table shows that the designers made trade-offs. External memory addressing for extra on-chip functions. Generally, the ability to expand memory off of the chip implies that a ROMless family member is available for use in limited production numbers, where the expense of factory programming can be avoided. Lack of this feature implies that the chip is meant for high production volumes, where the expense of factory program parts can be amortized over a large number of devices. 16-bit microcontrollers. 8-bit microcontrollers can be used in a variety of applications that involve limited calculations and relatively simple control strategies. As the requirement for faster response and more sophisticated calculations grows, the 8-bit designs begin to hit a limit inherent with byte-wide data words. One solution is to increase clock speeds. Another is to increase the size of the data word. 16-bit microcontrollers have evolved to solve high-speed control problems of the type that might typically be confronted in the control of servo mechanisms, such as robot arms, or for digital signal processing, DSP applications. The designs become much more focused on these types of real-time problems. Some generality is lost, but the vendors still try to hit as many marketing targets as they can. The following table lists only 3 contenders. Intel has recently begun vigorously marketing the 8086 family. Other vendors are expected to appear as this market segment grows in importance. The pulse width modulation (PWM) output is useful for controlling motor speed. It can be done using software in the 8-bit units with the usual loss of time for other tasks. The 16 and 32-bit controllers have also been designed to take advantage of high-level programming languages, in the expectation that very little assembly language programming will be done when employing these controllers in sophisticated applications. 32-bit microcontrollers, crossing the boundary from 16 to 32 bits, involves more than merely doubling the word size of the computer. Software boundaries that separate dedicated programs from supervisory programs are also breached. 32-bit designs target robotics, highly intelligent instrumentation, avionics, image processing, telecommunications, automobiles, and other environments that feature application programs running under an operating system. The line between microcomputers and microcontrollers becomes very fine here. The design emphasis now switches from on-chip features such as RAM, ROM, timers, and serial ports to high-speed computation features. The following table provides a general list of the capability of the Intel 80960. All of the functions needed for I/O, data communications, and timing and counting are done by adding other specialized chips. This manufacturer has dubbed all of its microcontrollers embedded controllers, a term that seems to describe the function of the 32-bit 80960 very well. Development systems for microcontrollers. What is needed to be able to apply a microcontroller to your product? That is, what package of hardware and software will allow the microcontroller to be programmed and connected to your application? A package commonly called a development system is required. First, trained personnel must be available either on your technical staff or as consultants. One person who is versed in digital hardware and computer software is the minimum number. Second, a device capable of programming EEPROMs must be available to test the prototype device. Many of the microcontroller families discussed have a ROMless version, an EEPROM version, or an electrically erasable and programmable read-only memory EEPROM version that lets the designer debug the hardware and software prototype before committing to full-scale production. Many inexpensive EEPROM programmers are sold that plug into a slot of most popular personal computers. More expensive and more versatile, dedicated programmers are also available. An alternative to EEPROMs are vendor-supplied prototype cards that allow code to be downloaded from a host computer and the program run from RAM for debugging purposes. An EEPROM will eventually have to be programmed for the production version of the microcontroller. Finally, software is needed, along with a personal computer to host it. The minimum software package consists of a machine language assembler, which can be supplied by the microcontroller vendor or bought from independent developers. More expensive software, mainly consisting of high-level language compilers and debuggers, is also available. A minimum development system, then, consists of a personal computer, a plug-in EEPROM programmer, and a public brand assembler. A more extensive system would consist of vendor-supplied dedicated computer systems with attendant high-level software packages and in-circuit emulators for hardware and software debugging. In $1990, the cost for the range of solutions outlined here is from $1,000 to $10,000. Summary: The fundamental differences between microprocessors and microcontrollers are: microprocessors are intended to be general-purpose digital computers, while microcontrollers are intended to be special-purpose digital controllers. Microprocessors contain a CPU, memory addressing circuits, and interrupt handling circuits. Microcontrollers have these features as well as timers, parallel and serial input-output, and internal RAM and ROM. Microcontroller models vary in data size from 4 to 32 bits. 4-bit units are produced in huge volumes for very simple applications, and 8-bit units are the most versatile. 16 and 32-bit units are used in high-speed control and signal processing applications. Many models feature programmable pins that allow external memory to be added with the loss of input-output capability. Answer the following questions. Name 4 major differences between a microprocessor and a microcontroller. The 8051 has 40 pins on a dual inline package DIP package, yet the comparison with the Z80 microprocessor totals 58 pins. Explain this difference. Name 20 items that have a built-in microcontroller. Name 10 items that should have a built-in microcontroller. Name the most unusual application of a microcontroller that you have seen actually for sale. Name the most likely bit size for each of the following products: modem, printer, toaster, automobile engine control, robot arm, small ASCII data terminal, chess player, house thermostat. Explain why ROM-less versions of microcontrollers exist. Name 2 ways to speed up digital data processing. List 3 essential items needed to make up a development system for programming microcontrollers. Search the literature and determine whether any manufacturer has announced a 64-bit microcontroller. This concludes Chapter 1.